Hello, this is Professor Matt Katroulis of Rio Hondo College, and this will be the video lecture for Chapter 4 for Chemistry 110 on the topic of energy and matter. A couple preliminaries before I start on this video lecture. First of all, I'm cutting out a lot of the topics which are more mathematical, largely because I don't feel that these are particularly relevant to the kind of material you need to learn. So just to give you an overview of what I'm going to be cutting, for section 4.5, I would like you to have a conceptual understanding of specific heat when we get to that. So know what a definition is, know what a large value versus a small value means, but we're not going to need to do any of those calculations. And then also in section 4.6, none of the calculations need to be known. And you can skip section 4.7 entirely. In fact, the only calculations that we're really going to look at will come up in just a few minutes here, and they're fairly simple. So the definition of energy is a bit abstract and requires studying thermodynamics in some depth to really get a solid grounding in, and it's not something that would be really worth it to us. But the technical definition is that it is defined as the capacity to do work. And we can define work as energy put to some useful purpose, directed energy. This is in opposition to the other form of energy, which we call heat, which is not directed to a particular purpose. We can look at energy in a couple of different categories. So first we have kinetic energy, which is the energy of motion. You'll recall that we used temperature values to compare relative kinetic energies. At higher temperatures, molecules tend to have higher kinetic energies on average, and at lower temperatures, the average kinetic energy is lower. And then another abstract concept would be potential energy, which is stored owing to something's position. So, for example, there are certain chemicals which contain a lot more energy in them than others. Fuels, for example, like in gasoline, contain a lot of energy stored in the positions of the atoms through their bonds, compared to other molecules like, say, nitrogen gas, which is very, very stable and has a low potential energy. We're going to be looking at a couple very important conservation laws in this class, and by that just means that something is going to stay constant. So the law of conservation of energy essentially tells us that energy is not created or destroyed in any chemical process. It can only be transferred from one location to another. So if you'll recall, when we started talking about electron configurations back in Chapter 2, we were also talking about excited atoms and atoms in the ground state. And you'll recall that we said that when an atom is excited, its electrons can fall from higher energy levels or higher shells to lower ones, and they shot off a photon of light as they do that. That is a consequence of the law of conservation of energy. The electrons can't just fall from higher levels to lower levels without releasing energy in some way. We're going to look at a couple different units of energy. Joules are by far the more common in scientific calculations, but calories, as I'm sure you've heard of course, are still very commonly used in this country. And the technical definition of calorie is, it is the amount of energy that you would need to raise the temperature of 1 gram of water by 1 degree Celsius. So if you wanted to raise the temperature of 2 grams by 1 degree Celsius, you would need 2 calories. If you had 10 grams of water and you wanted it to go up 1 Celsius, you would need 10 calories. If you had 1 gram of water and you wanted it to go up by 10 degrees, you would also need 10 calories. So for every 1 gram and every 1 degree Celsius, that's going to factor into the amount of energy you need. And you do not need to memorize this, but a calorie is equivalent to 4.184 joules. Now, the calorie I've just been talking about is probably not the calorie you're most familiar with, and that is a nutritional calorie. And we distinguish them by capitalizing the C in the unit. And so a nutritional calorie is really a kilocalorie. In other words, it's really 1,000 of these calories. So one nutritional calorie is a kilocalorie, is 1,000 of the small c calories. So whenever we're looking at a nutritional label on an item of food and it says that that item has, say, 100 calories in it, that is technically 100 big C calories. That would be 100,000 little c calories. Fortunately, when we talk about exercising, the same thing applies. So if you're exercising and it says you've burned 100 calories, you've really burned 100 kilocalories, the big C calories, and 100,000 little calories is what you have burned. So just watch out for the difference between the capital C and the little c. Now, when we look at those same food labels, we know that food is often divided into 3 categories in addition to vitamins and minerals. So the energy can be derived from protein, it can be derived from carbohydrates, as well as from fats. And each of these topics will have their own chapter towards the end of the course. So I'm not going to go too much into what they do and how they're structured just yet. But proteins and carbohydrates each have about 4 calories of energy for every gram that you consume. Fats, on the other hand, are much more energy rich, and that's why we have to exercise a lot harder to burn them off. So every gram of fat has 9 calories of energy in it. So this is really the only calculation from this chapter that you need to be able to know how to do, and that is to derive the total calories of a meal based on its protein, carbohydrate, and fat content. So let's say we take 1 serving of pasta, and a serving of pasta says it has 0.6 grams of fat, 14 grams of carbohydrates, and 3 grams of proteins. We want to know how many calories there are, and to keep significant digits simple, let's just round this value to the tens place. So let's go ahead and solve this question here. So we're going to go ahead and break all these down into their own categories. So let's start off with the amount coming from fat. So we have here 0.6 grams of fat. And we know that every 1 gram of fat has 9 calories in it, plus, now we'll go ahead and take care of the carbohydrates and the proteins. So we have here 14 grams of carbs times, well, for every 1 gram of carbs, there are 4 calories, plus the amount from protein. And so we have 3 grams of protein times the same factor of 4. So every 1 gram of protein has 4 calories. So if we look here, first of all, we've got 9 times 0.6. This would be 5.4 calories. Plus, here we have 14 times 4, which is going to be by far the biggest chunk. That is going to be 56 calories. And then here we have 3 times 4 is 12 calories. So adding this up and rounding to the tens place, this gives me 73.4. So rounded to the tens place, that would be 70 calories. I could ask you also what percent of calories come from each different category. So what percent of the calories, for example, are coming from carbohydrates? Well, that would be easy to find here. So the percent of calories from carbohydrates is going to simply be the part that comes from the carbohydrates, so that's 56 calories, over the whole of 70 calories. And let's say I want to go to 2 significant digits on this, even though that's technically only 1 there. So, and then we multiply by 100 to convert it into a percent. So 56 divided by 70 tells us that this is roughly, actually we only need 1 significant digit, this is 80% of the calories. I'm now going to go in another direction into a topic which I think is by far the most important topic in this chapter, and one that will have wide-ranging effects throughout the rest of the course, and that is the subject of intermolecular forces. And this follows nicely on our discussion of bonding. We can kind of think of it as being bonding light. So we know that bonds hold atoms together to form molecules in covalent compounds, and ionic bonds hold the crystal lattices together in ionic compounds. But what about between molecules? Are individual molecules bonded to each other? Not really. The term that we're going to use instead of bonding is going to be intermolecular force. So that's the attraction between 2 or more molecules. And we're going to have 3 different forces that we will look at. I want to start off with what are called dipole-dipole forces. Then I will talk about hydrogen bonding, which is actually a very strong type of dipole-dipole force. Unfortunately, that word bonding is confusing there. This is not really bonding. Again, this is an intermolecular force. And then finally, what we call the London dispersion forces. So let's start with the dipole-dipole forces. So molecules which are polar will attract each other through these dipole-dipole forces. So the definition of a polar molecule essentially is it is a molecule that has a dipole moment. And if we simplify this concept of dipole moment for just small molecules for the time being, what that means is that one side of the molecule is positively charged and the other side is negatively charged. For more complicated or larger molecules, there might be multiple sections which are positively charged and multiple sections which are negatively charged. And so we're going to use the specific terms partial positive for the parts of the molecule which are positively charged here, and partial negative. We can do this atom by atom, or we can just say this side of the molecule is partially positive and this side is partially negative. You will encounter both of those. So the regions that are going to be near the most electronegative atoms are going to be partially negative, and we'll generally label those with this little delta minus sign. And those near the less electronegative atoms are going to be marked as partially positive. So remember, fluorine is the most electronegative atom, so the closer an atom gets to fluorine, the more partially negative it is likely to be. So let's look at a couple examples here. So let's start with hydrogen chloride. Hydrogen is much less electronegative than chlorine. You don't need to memorize these values, but chlorine's electronegativity is 3. It's right next to fluorine in the periodic table. Hydrogen is quite a bit further away from fluorine. Its electronegativity is only 2.1. So that means this side of the molecule is going to be more negative, and this side of the molecule will be more positive. And we can indicate that with these symbols here. How about here? Fluorine is the most electronegative atom on the periodic table. So it makes sense that the electrons should be pulled towards the fluorines. And that would leave sulfur deprived of electrons and being the positive part of the molecule. So there's a couple ways we could note this. We could put the positive here and the negative here somewhere, showing that this whole side is negative. Or we could just do it kind of atom by atom, as I've done here, putting the positive on the sulfur and the negatives on the fluorine. Remember, these forces are particular to polar molecules. So here is an example. This is the molecule formaldehyde. Oxygen is more electronegative than carbon, and we've said that carbon and hydrogen with very similar electronegativities, 2.5 and 2.1, we're going to say that they are a nonpolar bond, a nonpolar covalent bond. So we don't have to worry about electrons being pulled one way or the other by the hydrogens. The electrons are being pulled towards the oxygen. So that's going to make the negative side be the oxygen and the positive side be the carbon. What that means is if you put two or more formaldehyde molecules together, here we see three of them, they are going to be attracted to each other. The negative side of one molecule is attracted to the positive side of the other, and although we don't have any symbols that to indicate that, sometimes we use dashed lines, this is going to represent an attraction. So a dipole-dipole attraction. Same thing here. There's going to be a negative attracted to a positive. And this pattern would just continue on. So this negative would be attracted to the carbon of another molecule throughout here. Now, as I said a second ago, hydrogen bonding is technically a type of dipole-dipole force, but it's very special, and so rather than use that definition of calling it a dipole-dipole force, we're going to give it its own category. Hydrogen atoms are quite small, and when they bond to very electronegative atoms, what happens is those small hydrogen atoms become just very tight little centers of positive charge. So they're not just partially positive, they're very partially positive. We don't really indicate that any different with our symbols, but it's just something we need to know. And since these are so partially positive, any electronegative atoms on other molecules are going to be very attracted to those, and they will form what we call a hydrogen bond. One more time, it is not really a bond, it is an attraction between different molecules here. So we need to be clear what we mean by very electronegative atoms, because right now that phrase is very vague. So it's only going to be three different atoms. Phone. So fluorine, oxygen, and nitrogen only when we talk about hydrogen bonding. So hydrogen atoms that are covalently bonded to fluorine, oxygen, or nitrogen can participate in hydrogen bonding. Hydrogens bonded to carbon, to sulfur, to bromine cannot make hydrogen bonds. Some people put chlorine on that list, but that's unusual. So we're just going to keep it phone, F-O-N. So we say hydrogens on the phone. And then when we look at the other piece of this, so the lone pairs of an F-O or N, not the same F-O or N, but somewhere on another molecule, they're going to be very attracted to those hydrogens on the phone. And that attraction is called a hydrogen bond. And we will not have any exceptions to these terms. Okay. So very, very critical. Don't confuse covalent bonds with hydrogens. So hydrogen bonded to fluorine, or hydrogen bonded to oxygen, or hydrogen bonded to carbon with a hydrogen bond. Those are still just plain old covalent bonds. So all the bonding that we learned about in the last chapter, those were ionic, and the ones we drew with straight lines were covalent bonds. They are actually sharing electrons, and hydrogen bonds are meant to be attractions between different molecules at a somewhat simplified level, and that's how we'll keep that for this course. So let's look at all the different possible ways this could happen. So wherever I've got a line here, this just indicates a bond to some atom, and it could be a carbon, it could be a sulfur, it could be something else. We don't really care. So wherever I haven't labeled this, that just means it's not really important. So all these hydrogens are on phones, fluorine, oxygen, or nitrogen atoms. So this hydrogen is very partially positive, as is this one, as is this one. All of them are very partially positive. So they're going to be attracted to molecules that I've drawn over here. So a hydrogen on a fluorine could be attracted to another fluorine atom, which does not necessarily have to be bonded to a hydrogen. This could be a carbon or something like that. Doesn't matter. So you see the H is bridged between these. Or that hydrogen could be attracted to an oxygen, or it could be attracted to a nitrogen. Any of these would be considered a hydrogen bond. How about hydrogen bonded to oxygen? Same thing. You're usually going to see this with another oxygen. So you'll notice you have a covalent bond, and then we're using dashed lines here to stand for our hydrogen bond. But it doesn't have to be to an oxygen. It could be to a fluorine or to a nitrogen. And then finally we look at the same concept here, the hydrogen on a nitrogen. And when I say on a, I mean covalently bonded to a nitrogen. Could be attracted to the lone pairs of some other nitrogen, or they could be attracted to the lone pairs of an oxygen or a fluorine. So there's technically only 9 possible combinations here in terms of where we could observe hydrogen bonding. So let's look at what is perhaps the single most important instance of this, and that is with water. So here I have 2 water molecules. Remember, these lines are covalent bonds, and these oxygens have lone pairs. The hydrogens are very partial positive, okay, because they're bonded to very electronegative oxygen atoms. And since this hydrogen here is very partially positive, it would be very attracted to oxygen, which is partially negative. And again, we've used dashed lines here. There's no universal symbol. Some people used dotted lines. Some people don't use any lines whatsoever to indicate this. Now, let's say we put lots and lots of these water molecules together, and then we lower the temperature. What does that mean again? Lower temperatures mean that the molecules have, on average, less kinetic energy. They're not moving around so much. And what happens when we lower the temperature of water substantially? It eventually begins to freeze. And so this is what we get with ice. Every one of these guys right here stands for a water molecule. And so we see the oxygen here is attracted to the hydrogen, the partially positive hydrogen. Here we're using these dots to stand for the hydrogen bonds. And then that pattern continues. And you'll notice if you look carefully that we get what look like hexagons here. So there's like a hexagon right there, and then here's another hexagon, and then another hexagon right there, and that pattern continues and continues. I would encourage you to go and do an internet search on snowflakes, and you'll see that the vast majority of snowflakes have a structure which contains 6 points and or hexagons in them. And that is a consequence of the way that these molecules are attracted to each other. It's also a very important aspect of what's holding DNA molecules together. There's actually a couple attractive forces that hold the 2 different parts of DNA together. We would use the word strands here to describe those. And if we look very closely at the atoms that are in the middle of DNA here, you'll notice that this is an oxygen. It has 2 lone pairs that we're not showing. Here is a hydrogen bonded to N, so it's on the phone. So this hydrogen would be attracted to this oxygen. Likewise, this hydrogen, because it's fairly close to this nitrogen, would be attracted. And then this hydrogen here, which is on nitrogen, could be attracted to the lone pairs of this oxygen. We call this base pairing when we look at DNA. Same concept down here for another pair of what we call bases in DNA. So hydrogen bonding is very important in biological molecules, and it's very important in the natural world around us. Very critical. So let's take a look at some molecules here. So the first question I would have for you here is, which of these molecules can hydrogen bond with water? With water. Now remember, water has both parts, both components to it for hydrogen bonding. When I say that, what I mean is that water has both the hydrogen, which is bonded to a phone, F-O or N, and it has an oxygen with lone pairs. In order to make hydrogen bonds, you only need to have one or the other when you put something in contact with water. So what we need to do here is just look and see, does it have either one of those characteristics? So first of all, we have CH4, methane. And if you draw the Lewis structure of CH4, you would see that all the hydrogens are bonded to carbon atoms. Carbon is not very electronegative, so none of these hydrogens are on the phone. They are all sharing electrons happily and fairly equally, so there's no partial positive here. So none of these hydrogens here would be attracted to the oxygen in water, and similarly there's no phone, F-O or N, to be attracted to the hydrogens of water. So this molecule here, methane, will not hydrogen bond with water. What about NH3? You'll remember that the name of that is ammonia. So the first thing that we would ask ourselves is, are there any hydrogens on the phone? And the answer is yes. This hydrogen is bonded to a nitrogen. So this hydrogen, and this hydrogen, and this hydrogen would all be attracted to water molecules. I could draw here a water molecule. And we would see here that this is positive, this is partially negative, and these would definitely be attracted to each other. Not only that, you also have a nitrogen with a lone pair, so this nitrogen could be attracted to the hydrogens of some other water molecule. So we would definitely expect there to be attractions between ammonia and water molecules. How about formaldehyde? We saw this a moment ago when we were talking about dipole-dipole forces, but now we're talking about this with water. So first, do we have hydrogens on the phone? Well, these hydrogens are bonded to carbon. That means they are not partially positive like the hydrogens that were in ammonia. But they do have an oxygen with lone pairs. So that means there will be the attraction of those oxygens to the hydrogens of water. But it's not going to be entirely reciprocated. These oxygens are not going to be attracted to these hydrogens. But the answer is yes, they can form some hydrogen bonding with water, just not as versatile as ammonia was. HF is going to be just like ammonia in terms of its ability to hydrogen bond. it has both pieces. Meaning, first we have a hydrogen on the phone, hydrogen bonded to F. So that means this hydrogen would be very partially positive, and it would certainly be very attracted to the lone pairs of a water molecule. Which are partially negative. And similarly here we have a fluorine which is very partially negative, so a phone. It would be attracted to the hydrogen of a water molecule. Which is partially positive. So of these four, only methane is entirely unable to make hydrogen bonds with these compounds. Okay. You will notice that they all have dipoles, meaning they all have positives and negatives, all of these molecules here, except for CH4. So they also have dipole-dipole forces. But ultimately, the important force for these molecules is, at least for NH3 and HF, is going to be hydrogen bonding, at least in the context of water. Now I'm going to change the question up a bit. So, of the ones that could hydrogen bond with water, that would be these three here, which of them can hydrogen bond with other identical molecules? In other words, can NH3 hydrogen bond not with water, but with other NH3s? Well, let's draw some Lewis structures here. So I'm going to draw it sideways, which is fine. There's no rule that says the lone pairs always have to be up. So we know that the nitrogen is partially negative, and the hydrogens are all partially positive here. And then I can go ahead here and put a nearby molecule. And again, the nitrogens are partially negative. The hydrogens are positive. I don't have to do that for every single one of these normally. But I would definitely expect there to be an attraction between those. So there's a hydrogen bond. So NH3 can hydrogen bond with water, and it can also hydrogen bond with itself. With formaldehyde, that's not going to be possible. Because as we already saw, all of the hydrogens are bonded to carbon. Therefore, you're missing one of the pieces that you need for hydrogen bonding. You need to have a hydrogen on the phone. So if I put this next to another identical molecule, none of the hydrogens would be attracted to these oxygens. So yes, formaldehyde will hydrogen bond with water, but it can't hydrogen bond with other formaldehyde molecules. Finally, if we look at HF, hydrogen fluoride, we see that hydrogen is positive and fluorines are partially negative because they're so electronegative. So this is partially positive, this is negative. So we have hydrogen on the phone, and we have some other phone, FO or N, so definitely. HF molecules can hydrogen bond with other HF molecules. Not a problem. Incidentally, when we're talking about hydrogens on the phone, fluorine is going to only make one bond in all of its compounds. And as we know, hydrogen only makes one bond in all of its compounds. So the only hydrogen on FO or N that we're ever going to be concerned with is HF. So that's a pretty limited sample that we have to worry about there, because it's the only molecule that will have both those parts.